This video is about flow control, one of the basic building blocks of reliable, efficient communication. It describes the basics of flow control, as well as its simplest implementation, something called a stop and wait protocol. The basic problem flow control tries to solve is when a sender can send data faster than the receiver can process it. So here we have a case where the sender A can send some 500,000 packets per second, but the receiver B can only receive 200,000 packets per second. This might be because B has a slower processor, its networking card isn't as good, or for whatever reason. And so the issue is that if A sends data at this full rate of 500,000 packets per second, then 300,000 of those are going to have to be dropped at B. That is, B will not be able to process them, and so only 40% of the packets will come through. And so there's a lot of wasted effort on A's part. It's a lot of wasted effort in the network. And it's also going to completely saturate B. So there's no reason for A to be sending data faster than the rate at which B can receive it. And so the basic approach that flow control takes is to make it so that the sender doesn't send packets faster than the receiver can process them. And the way this usually works is the receiver gives the sender some kind of feedback, whether it's implicit feedback or explicit, whether it's to slow down or speed up or to set a rate. So two basic approaches used in most protocols today. The first, stop and wait, I'll talk about in this video, which is very simple to implement, very simple finite state machine. The second is what's called sliding window, which I'll talk about in a later video, which is a bit more complex, but can provide better performance. So just a refresher on finite state machine diagrams. So when we draw a finite state machine of a protocol, we show the states that it can enter. Here's state 1, state 2, state 3. And then edges between the states have two pieces of information. First, the event that can cause a state transition on top, and then below, the action the protocol takes on making that state transition. The stop and wait algorithm is very simple. It has at most one packet in flight at any time from the sender to the receiver. So the basic algorithm is a sender sends one packet. It then waits for an acknowledgement from the receiver. When it receives the acknowledgement, it then, if it has more data to send, sends another packet. If it waits for some time and reaches a timeout and hasn't heard an acknowledgement, then it assumes that the packet has been lost. It has left the network. It was dropped on a router, or it was dropped to the receiver, something happened, and where the acknowledgement was dropped. And it resends the data. So there's a timeout, at which point it tries again. That's the basic algorithm. So the receiver has a one-state finite state machine, which is wait for packets. When it receives new data, it sends an acknowledgement, or when it receives data, it sends an acknowledgement for that data, and if the data is new, it delivers that data to the application. The sender finite state machine has two states. In the first state, it's waiting for data from the applications. This is where it's ready to send, but the application has not yet provided the data to send. When the application calls send, the protocol sends a packet with that data, or as much as it can fit in a packet. It then enters the wait for act state. In this state, there are two transitions. The first is if it receives an acknowledgement. If the protocol receives an acknowledgement, then it does nothing and goes back to wait for data. If there's more data to send, it'll send new data. Or if there's no more data to send, it'll wait until the software calls send. The second transition is when there's a timeout. So this is the case where it has sent a packet of data, but it hasn't received the acknowledgement. It's waiting and it's waiting and it's waiting, and it times out. So then it just tries resending. So it wants to pick this timeout so that it's conservative. It's pretty sure that the data or the subsequent acknowledgement has been lost. So it only has one packet in the network at any time. So that's the basic stop and wait algorithm. So here are four sample executions. The first is when there's no loss. Everything works perfectly. The sender sends its data, the receiver receives it, sends an acknowledgement, and now the sender, if it had more data, could send more. Second case, data is lost. Now the sender sends data, it's lost in the network, and so the sender times out and tries resending the data. So it's sitting in that waiting for act state, the timeout hits, and it resends. Here's a third case where the data is successfully delivered, but the acknowledgement is lost. And so now the sender is in the wait for act state, it times out, it resends the data, and then this causes the receiver to send a new acknowledgement, at which point then the sender gets the acknowledgement and continues as in the first case. So the fourth case is a little more complicated and actually shows a failure with the basic algorithm as I described it before, which is the sender sends some data and the receiver sends an acknowledgement. But let's say something happens in the network. Suddenly a link becomes very slow, or there's a big queue somewhere in the network, and the acknowledgement is delayed past the time of the timeout. And so the sender sends some data, an acknowledgement comes, but the sender resends the data before the acknowledgement arrives. The acknowledgement then arrives very shortly, and so now the sender knows that the data was acknowledged, and it sends another data packet. But let's say that in fact this data packet is lost. So now this first retransmission of the first data packet arrives at the receiver acknowledges it. The sender doesn't know whether this acknowledgement here, this ACK, is for the retransmission here of the data, or it's for the new data packet. And so here we can have an error, where if it assumes it was for the retransmission of the old data, it suddenly has to keep track of that, something the finite state machine needs to keep track of. If it assumes it's for the new data, that data might not have arrived. It could be assuming that data has arrived, which hasn't. So this is a basic problem that comes up in any reliable protocol. It comes up in flow control, which is how do you detect duplicates? How do you know when acknowledgements are from retransmissions or duplicated copies of packets versus new data? And so in the case of stop and wait, we can solve this problem with a 1-bit counter. And so the idea is that use this 1-bit counter on all data acknowledgement and acknowledgement packets. So a sender sends data 0, then it receives ACK 0. Data 1, ACK 1, data 0, ACK 0. Right? And so now the receiver can tell if this is new data or a duplicate. And so in that prior case I showed, it would be able to distinguish between the acknowledgement for the retransmission of packet 0 and an acknowledgement for the first transmission of packet 1. Now, a single bit counter makes a couple of simplifying assumptions. This doesn't work all the time. Like, what if a packet is delayed for many round trip times? It could be, for example, that this data 0 is delayed all the way to here, and then the receiver ACKs it, but it turns out it's actually just a copy of old data. And so this particular 1-bit counter approach makes two simplifying assumptions. First, the network isn't duplicating packets itself. Second, the packets are not being delayed for multiple timeouts. Now you can solve these problems by increasing the sequence number space, but for the simplifying assumptions to the simple protocol operating environment, this 1-bit counter can help a lot.